absolute value, right? Is how far the particle has moved in that time. And the actual field that we measure over here is the field as though the situation were static and the particle were at this position and not that position. This point out here doesn't know that the motion has changed if the motion has changed. So this guy here can pull a little feint and at a particular moment look as though it's going that way. And then an instant later it can say, oop, nope, I'm going to go the other way. Right? But the potential out here is as though believes that this particle has moved all the way from there to there. It is not. An instant later, it finds out, oops, wait a minute, you changed direction. You're over there now. Okay. But the potential that's seen is as though it's on the projected position where it would be. Yes?
So does that mean if this particle keeps instantaneously changing velocity, at the other point it looks as if the particle is just hopping between 2 points?
Yes and no. In order to do that, it would have to change its velocity instantaneously.
That's what I meant, instantaneously change.
So you have a problem with infinite forces and acceleration there.
Yeah.
Right? So it actually appears as though the particle is moving back and forth a larger distance than you might think, but you see the intermediate positions because the acceleration of the particle.
Yeah, I was just thinking if you could make it instantaneous.
If you could, it would just pop from there to there. Yes.
That would be entertaining, but
you
impossible.
can't.
Yeah.
So. Oh, I had a nice picture that I lost. All right. So now what does the potential look like if I plug this in and I want to find out what the fields look like? So I might start out and I would solve for, I'll write it V, the potential at position x and t and x, for example, right? And then from that position, then I'll find my electric field. But we have to be a little, actually, I have to get the rest of it. A of x and t. All right, so I've just written out my 4 vector there. And the electric field is going to be given by gradient of V minus gradient of V, I think, plus dA dt. I don't remember whether there's a plus or a minus sign in there. Actually, I've got it written down here somewhere, so don't worry. I will just check. Minus. Okay? So if I can find these, then I can find the electric field, and I can find the magnetic field.
Curl of paint.
It's got more than that.
Thank you. Yeah. That's what I have written down. Okay. So let's just start out and find the potential under this approach.
Is a 4 vector in this case, right?
A, as I have written it here, is a 3 vector.
Okay, that's
and
right.
V is the 4th term
Right. Okay.
in the 4 vector. Over here, I was trying to save some chalk,
Right.
and I wrote it as mu just to say we do this with each term in the 4 vector.
A needs a 1 over C in front of it. The A dt needs a 1 over C.
That sounds right. Thank you. Okay?
Now that makes perfect sense.
B is right.
I changed the equal signs. Yeah.
there no symmetric quantity for time changing potential generating part of the magnetic field?
No.
Okay.
Because there are no magnetic monopoles. That's why there's not symmetry there.
Oh,
So mathematically, it should be there. And I'm actually pretty sure there are physics theorists out there who include that term anyway. Because it should be there, mathematically. And maybe we'll find a monopole one of these days.
Not in California.
Okay. So there's my 4 potential over here, which means that I could find I'll get it, the electric potential, V, using that. I've got a C in there somewhere, so that's going to disappear. And I'm just going to end up with integral of rho of r prime t prime dv prime over r minus r prime. Now, you might think that this is just going to result in, if I take a point charge, I just put my point charge in there, the point charge comes out of the integral, and I just end up with, I should just end up with Q over R minus R prime. In static form, that's what we would get. Q over R minus R prime. It's the potential, okay? But not so fast. We have a problem here because we're integrating over a volume, and we're integrating over this primed volume, and one side of the primed volume doesn't send its information at the same time to the observer as the other side of the primed volume. So a correction has to be made to the volume, right? And that integral of 1 over 1 minus 1 over r minus r prime has to be corrected. And so the actual form, maybe because you guys in the back have trouble seeing the bottom of the board if I go up, is going to look like this. At the observation point, right? That's what you would have thought. Actually, I'll put the Q over here. And then there's a correction. The correction looks like this. 1 minus, I'll have to define a term here, n dot v over c. Oops, v prime over c. That's the velocity with which the source is moving. And I'm going to define as r minus r prime over magnitude of r minus r prime. Okay? So it's a vector that points from the origin, from r prime, the source, to the observation point. So this is just something that points in that direction. Okay? So this is what the potential from a point charge looks like now. Well, we made the correction for the motion of the volume, for the change in the effective volume due to the motion of the charge. And I have a whole page of arithmetic here that I am skipping. And I'll state that when we think about the charge moving along a particular direction, so the charge is moving like so, and my observation is is over here. So here's my source. It's moving with some velocity in that direction. And I have an observation point over there. Okay. Then and this distance here, from this point, from the distance from the projected point to the observation point, I'll write as just capital R, so that's R minus R prime. Okay. That potential then comes out to be now I have to think about the direction about sine theta. Sine theta is the angle between, so I've got n, that's a vector that points from r prime to r. Okay, so sine theta is, I'm just trying to remember whether it's this angle or that angle. I'm going to say it's this angle. And I will check it. Yeah. Did I screw up?
That expression doesn't have the right units, I don't think.
E squared over c squared. You're right. I've got an extra factor of c in there, don't I? Is that what you're saying?
Yeah. I think maybe if it was like c squared minus b squared sine squared theta.
Potential is just q over r, right?
Yeah.
That makes it right, dimensionally.
Yes.
Let me go back a page and see where I gained a factor of c.
Isn't there a 1 over c in front of those integrals? Like,
There's 1 over c here.
I think it might be. There's a lot of 1 over c in front of it.
Yeah, there's a, well, it's C row. It's C row. That's where you drop
It is
one.
c row? Oh, you're,
Yeah, the J0 is C row. So we lose the 1 over C with the C row.
Okay.
No, you lose the 1 over C because of C row.
I lose the 1 over c over there.
Because of C row. Because it's C row.
J has c row, yeah.
J0
okay.
is C row.
So then the 1 over c cancels out.
So there is no C. That's
So
what we're
that's,
saying.
yeah, that's the
That's
way I
right.
wrote it.
Yeah, that's what we're
Because I
saying.
wanted it to look like that. All right, yeah. So I may have not dropped a C that I should have dropped over here. I just went back a page. And yeah, I see where I failed to cancel out a C in my earlier steps. So it's this. Yeah, and in fact, on the next page, I wrote it correctly. So it was like just that equation that I copied for you that I failed. Oh, so I can remove this and make it an equal sign. All right. So now I've got to take derivatives of this in order to find the electric field that we actually observe. Let's see. Don't need this. I'll leave this up, that's my definition. I don't need this. We'll keep that. Oops. I'll leave it in this form. And this one is properly has the C's where it should be. I've defined N here, so I'll just leave it like that. Okay, now I want to find the fields. So that's all that's left. I have to do that. That derivative is complicated. Oh, I fixed this, so this is an equal sign here. Once again, by the fact that there's this screwy relationship between the space terms and t prime. Okay, so when we take the gradient in order to get the field, it's going to come out complicated. And I'm going to write out the complication, and then we're going to simplify. All right. So, gradient of v, so that's just that term, right? We're going to have to take a, right? Is, I'll just write it out. Q times b prime minus n hat dot b prime in the direction n hat over that's the first term. Next term. So basically, you've just got to use the chain rule here with the complication that when you take a gradient, you're going to be taking gradient of t prime. That's going to add terms. Product rule. Product rule. This is a B. Second term. Now for the next 6. That was good. But it's pretty sad anyway. Okay, the first term comes from the explicit R dependence of this term in here. Okay, I've got an R in there. When I take my gradient, I'm going to end up with the derivatives of that. Okay, so that's my first term. My second term comes from the explicit R dependence of this. So first the derivative of this, then the derivative of that times the other, right? So that's those two terms. And that term comes from the implicit R dependence of t prime. If we actually have to go ahead, and there's actually two differentiations that remain to be done down over there, okay? And that is then the gradient v term that comes out of plugging that potential into this gradient, okay? And then I'm going to have an A term that comes from the motion of the charge. And so there are going to be several terms here. And I just wrote that out to show you how many terms there are, and that we actually have to take more derivatives in order to get the full expression. What I'm going to do now, this is where the hands would come in handy, all right, is perform, I'm not going to do it, I'm going to state that what we did was perform that last derivative over there, get those terms, and then we look at it and it's a horrible mess, actually. Things don't drop out. But what we're going to do is say, if we get far enough away, then then we take a look at this and we see, oh, this one just drops off as 1 over, well actually this one drops off as 1 over r squared. All right? Why do I have 2 of those? So it looks like 1 over r squared. All right, I'll just make that argument for now and then we'll check it later.
You should have 2 of those.
Yeah, okay, 1 over r squared.
That's how Ohanian wrote it, for whatever reason.
This one's 1 over r squared. This one, we're going to find out that there are just 1 over r terms in there. All right? So we get far enough away, and the 1 over r squared terms drop out, and we just have the 1 over r terms remaining. So, magic occurs. And we end up with q over c squared times.
Professor,
Yes.
I can't see because of my angle on that board, but is the v vector over c the last term? Is that a v vector prime or a v vector? It's difficult.
Let me just check something here before I.
I can't really tell because of my angle.
Yeah. Okay. We're fine.
It's a problem.
Yes.
This gradient that we're taking, is this is in the,
It's a real space gradient
but is it for the primed coordinates or the unprimed coordinates?
for the unprimed coordinates.
Oh, okay.
No, it is the unprimed. That's what I've been working with gradients in the unprimed coordinates all along.
Okay.
So, Professor,
Okay.
what Josh was asking was the v in the dt prime frame, was that the v with the line through it because the board switches? That's a v prime.
That's
It's
a
the-
good question.
It is v prime. I'm looking at Ohanian.
You
It's
can
V
look at
prime.
Ohanian and find that it is V prime.
Yes,
Then I will take it as V prime. Let's see.
because it's all of those terms.
I've
are
got it
prime.
as V prime here in my notes as well. V prime.
Yeah.
Yes. Actually, there isn't a V.
Yeah.
It's just the charge that's moving. And we can always find a frame to observe things in such that it's only the charge that's moving.
And I'm almost out of internal memory.
Yeah. So I would actually just have, this is good, all right, it's working the way I want. If I don't have any acceleration in my problem, if my charge is just moving along at a constant speed, I don't have this term